say how exactly things are going to happen?
Can you give
Can
the
I give
intro?
you?
The intro.
Why should I do the intro?
Hi, Dr. Charles.
I don't know the.
I do. Yeah. No, I didn't. I didn't.
Yeah,
Okay.
see, that's what I'm
Anyway.
thinking.
Yeah. Good evening, everyone, and welcome to the IAU GA 2024, to all of our public and all of our delegates, our participants. We're going to get started in just a bit, but I'd just like to first announce if all of the people behind the sound desk could please come to the front here. So we're just a bit more all together here. So those sitting in behind the sound desk, please could you make your way to any of these seats in the front. Thank you.
Where was I put this word there?
If everyone would please take your seats, we'll begin in 2 minutes. Thank you. We'll get started in 1 minute.
Shall I? Shall I settle them now?
Yes, yeah. Put them in their place. Then that was for me.
See, they need to turn up the lights now because the darker person has come to the stage. A little bit brighter. You guys can come and settle in. We're going to start now. Are you guys ready? You ready for an evening with NASA? Have you ever imagined that you would be like saying to your family and friends, I'm going to go out for an evening with NASA now? Did you know that NASA is one of the most recognizable brands in the entire universe? So, welcome everyone on behalf of the organizing committee of the International Astronomical Union's General Assembly. So I'm the chair of the organizing committee. We're having this big conference here. It's the biggest astronomy conference in the world, and it's for the first time on the African continent. That's why it's time for Africa. Yay! And I'm super grateful to our colleagues at NASA because they came in force. They came with all their big guns. And it, just having NASA at an event, I don't know if you guys realize, Alex, how significant it is for young people, for people all over the world to be able to have this opportunity. So thank you very much, Alex and Mark and all your colleagues. I'm going to hand over now and enjoy the evening with NASA.
For those who don't know, that was Kevin Govender. He introduced himself, but without his name. So round of applause for Kevin. I'm Alex Lockwood. I'm the Science Engagement Lead at NASA, and it is my pleasure to bring you an evening with NASA. We have 7 dynamic speakers and then a special presentation at the end. And first up is our Director of Astrophysics, Dr. Mark Clampin.
So, our way. Did I get that right? So it's a great pleasure to be here at the very first IAU meeting in Africa, and we're all really excited. I want to thank Kevin and Alex for the introduction, and especially want to thank Kevin and his team for organizing a really great event. So we're really pleased to be here, and we're really excited to tell you about NASA. And I will correct Kevin just a bit. We actually brought our big telescopes. So how do I move this, guys? Okay, it's a little slow. So I'm the Director of Astrophysics, and what I'm going to talk to you tonight is what do we do in astrophysics, and what is NASA's role, and how do we pursue the study of astrophysics. So we try to answer 3 basic questions in the NASA astrophysics program. Very simple questions. The first one is, how's the universe work? Does anybody know? I have one taker there. So what we try to do there is really understand the origin and destiny of our universe, and that means that we need to understand things like black holes and how they work, what is dark energy, what is dark matter, and how does gravity work. We also try to understand how did we get here, and that means understanding the origin of the universe and the origin and evolution of the galaxies and stars that we see making up our universe. And then finally, the other question is, are we alone? And this is a really pertinent question right now, and you'll see why as I go through my presentation. And what we try to do is discover planets around stars that you can look up in the sky at night and see. And then we try to understand whether there's evidence that life could be present on the planets around these stars. So, first thing is, how do we know what to do? I just showed you our 3 goals, but how do we know what missions to build or how to do things, what we should pursue and what we shouldn't? And the way that it works for NASA is that every 10 years, we get a report from the National Academies of Science. And they tell us what to do in that decade. And they make a recommendation on the big mission that we should build. And they tell us what science we should be working on. And this system works really well because it tells us what we need to do, so there's no doubt, no fuzz, we have clear marching orders. And it also tells stakeholders in Congress what they should be funding. So it's a really nice system that works and helps us make progress as we go through the decade. And this is a really great process because in 1972, they recommended the Hubble Space Telescope, and we built the Hubble Space Telescope. And it goes on. In 1982, they recommended the Chandra Space Telescope. In 2001, they said, go ahead and build the Webb Space Telescope. And that's what we did. And right now, we're in the process of building and constructing the next of these missions, which is the Roman Space Telescope. And I'll talk a bit more about that. And then we'll get to the recommendations for this decade towards the end. So this is what we currently are operating in astrophysics. This is what we call a swoosh chart, or a more mundane name is the astrophysics fleet. And we've got 3 different colors there. So the purple ones are missions that we built, and they've exceeded their nominal operating lifetime, but they're still working, so we continue to operate them. The green ones are missions that we've just recently flown, and obviously James Webb is there. It's been in orbit for just over 2 years now. And the other 2 green ones illustrate a big part of what we do, which is partnering with our international partners. So the Euclid mission there, we partner with the European Space Agency, and on the XRISM mission, just under it, we partnered with our colleagues in Japan to build an X-ray telescope. And then you see these orange and gold missions here. These are all things that we're currently building or starting to design. So we're always trying to maintain a balance between what we've done before that still produces science and what we need to do for the next generation of astrophysicists and scientists. So I'm going to just tell you a few words about some of the missions that we're really proud of. I can't cover them all because you just saw in that chart. There's a lot. But the Hubble Space Telescope is everybody's favorite. We've all seen an image from the Hubble Space Telescope. And the image that I've got here is what in science we call a really sort of seminal observation, which is the Hubble Deep Field. And this was the brainchild of a colleague of mine, Dr. Bob Williams, who wanted to know, as the director of the Space Telescope Science Institute, what would be seen if we pointed the telescope in one place for an extraordinarily long time. And most of the science community told him, no, don't do that, it's very risky, you know, just keep doing the science programs you're doing. And he decided that we would take this scientific risk and spend something like, I think, 300 hours of Hubble time staring at what we thought was a blank piece of sky. And lo and behold, this is what we found. Tens of thousands of galaxies. And this has completely changed how we see the universe and how we understand how galaxies formed and evolved over the history of the universe. It also led to the birth of the James Webb Space Telescope. So, James Webb is currently our main operating mission. It's an infrared telescope, and what that means is it sees heat radiation. And that's a very challenging observation to make, because if you want to look in the infrared, you cannot be warm yourself producing your own heat. So we had to figure out a way of making James Webb very, very cold. So it's actually 40 degrees above absolute zero, or about minus 400 degrees Fahrenheit. And the way we get it that cold is by basically flying it with this big shield that you can see underneath that blocks the sun from seeing the telescope. So the telescope's just thinking of the colder space, and it cools all the way down to about 40 degrees above absolute zero. And that means that we can then study all the way back to the origins of the very first galaxies and stars that formed in the universe. And because they're they formed at such an early time in the universe, the space is stretched, and so the light coming from these objects is only seen in the infrared. So it's Webb's second anniversary, and we're really excited about the science that it's been doing. And this image was the second anniversary image of the James Webb Space Telescope. And it's kind of neat. I'll go back see if I can get it to go back, because we start with the Hubble image, which we see in visible light, and then when you see the line go across the screen, it changes to Webb's infrared view of this object. And it's really highlighting the regions of star formation where these two galaxies that are merging are basically creating new areas of stars, basically as the gas is sort of compressed in waves. So this is a really exciting image, and it's given us lots of new information about how galaxies merge and how they create new stars as they collide. We also have the Chandra Space Telescope, which is an X-ray telescope. So it basically works at the same wavelengths that are used when you go to the doctors to get your arm X-rayed if you've just sprained it or broken it. And it sees extremely high energy events like black holes. So this is a great example of how we use Chandra. We, in fact, with this particular observation, saw this object with the James Webb Space Telescope, and we wanted to understand whether it had a black hole at its core. And so we looked at it with Chandra. So we basically bring the value of all these different telescopes together. And lo and behold, one of the reasons this object is so luminous is because it has this massive black hole in its core powering the system. We also build smaller missions as well, and these missions are very unique because they're a competition. So we don't just, for these ones, take direction from the decadal. We take direction on the science theme, but then we let teams compete to build these missions, and they all submit their ideas, and we pick the very best ideas. And TESS here is a really great example. So this mission measures mini eclipses. So when planets cross the face of a star, they cause a very small dip in the light coming from that star. And this is a way of discovering planets around other stars without ever actually taking an image of the planet. And once we've done that, we can then repeat the observation, breaking the light into its constituent wavelengths, and that tells us something about the atmosphere. So TESS was built to find small rocky planets around nearby bright stars. And you can see from this tremendous planet count here, it's been wildly successful. 543 confirmed planets, and then it's got another 7,000 that we haven't even had time yet to confirm as exoplanets. So it's producing a lot of really great new science. Whoops. Okay, I'm going to skip over that one because the noise is a little much. One of the things that we do and where we have collaborated with our colleagues in South Africa is our balloon program. So when we build these very big missions, we kind of need a specific set of expertise and skills. And one of the ways that we get there is by training our early career scientists on programs like balloon flights. So these balloons are very large. They can fly for many days. We just set a new record at Christmas with a balloon that flew for 57 days. And they do specific measurements. And in addition, they allow us to train early career scientists and early career engineers. And they also allow us to test new technologies. And those technologies are then used in missions that we fly into space. So the balloon program is a very important part of what we do. And we fly balloons regularly from Wanaka in New Zealand, where they circumnavigate the sort of southern globe. And we also occasionally fly them from McMurdo in the Antarctic. And those balloons go probably 1 or 2 a year, and they circumnavigate the Antarctic continent while they're making their measurements. And we generally focus on infrared observations from the Antarctic flights. So these are a really important part of our program, and it's how we train people, how we develop technologies, and also do measurements that we don't actually need to go into space for, but are important scientific investigations. So I mentioned the Nancy Grace Roman telescope. This is our next big program. It's called a flagship, and this is a real change in how we do science with astrophysics at NASA. So most of those missions you've seen so far, like Hubble or Webb are really what I think of as point and shoots, like when you take a snapshot with your camera, your phone. This mission instead is doing a survey, so it's more like doing a pano shot with your iPhone where you scan a whole region of a target, whether it be a vista looking out over the sea or a group of friends standing across the room. This mission basically studies the sky and collects image after image, so it's eventually tiling its way across the sky. It produces a really large amount of data. It's about the same size as the Hubble Space Telescope, but it's much more sensitive, and we're going to use this mission to understand how dark energy and dark matter work. It's also going to allow us to study all these other subjects. So one of the things we really like with NASA is when we build a telescope to do one science problem, and then we get all these other ones for free. So you can see some examples here. Astroseismology, what's that? Well, it's studying the oscillations of stars, and this is very important as we try to understand which stars can have planets and which ones can't. It also allows us to look at how galaxies assemble, so we can map out galaxies and the outer regions as well, study the constituent stars in those galaxies. So this mission will really allow us to do a lot of new science that we've never been able to do before. It's also a challenge because it produces petabytes of data, and all that data has to be processed and analyzed, and there's so much of it, you can't just download it onto your home computer. You have to basically take yourself to the data by working in the cloud instead of bringing the data to you. So that's a real sort of mind change for how astronomers do science as well. And then finally, I'm just going to finish up by telling you about the next big thing that we're planning to do. And the younger ones here will probably see this thing launch. We expect it's going to take something like 15 or more years to design and build. And this is what the National Academies told us to do this decade, and that is search for life in the universe. So we have got direction to build a telescope that will search the nearest 300 stars to our own solar system, and around each of those stars look for small planets like our own planets, what we call pale blue dots. When we found a sample with this telescope, we'll go back and analyze each of those small blue dots to see if there is evidence of life on those planets. And we do that by looking for specific chemical signatures in the atmospheres that we call biosignatures. So this is going to be a big telescope, 6-7 meters in diameter. Unlike the Webb, it's going to work in visible light, same light you're looking at me with. And it's going to be the next big challenge. And the challenge here is that this telescope has to be able to look at extremely faint objects. And you probably remember that Hubble image I showed you. So some of the faintest objects in that Hubble image of the Hubble Deep Field are about the same brightness as the planets that we're trying to image, and yet they're right next to some of the brightest stars in the sky. So we have to figure out how we can block out the light from the central star by factors of 10 billion. And you can figure out how we're doing this very simply. We're using an instrument called a coronagraph. And a coronagraph blocks out light from the central star and allows you to look at the region around the star. And this technique was invented, believe it or not, in 1935 by a French astronomer who wanted to study the sun, but he didn't want to wait every 10 to 15 years for an eclipse. So he kind of built his own eclipse machine called a coronagraph. And this is what we will now use to look for planets. And you can get a rough idea of how this works because you can hold your thumb up to one of these flashlights and see the structure around it, whether it's a mountain frame or the ceiling of the building. So imagine trying to do that, but reducing the light from that central flashlight by a factor of 10 billion. So it requires us to go to new levels of stability with a telescope that we've never been before. 1,000 times more stable than the James Webb. We have to improve the quality of the image by 1,000 times and keep it that way over the whole time we're exposing. So there's a lot of really interesting scientific and engineering challenges in this mission, and we're really looking forward to taking them on and figuring out how to build this mission. And with that, I will finish. I'm going to skip this one and hand over to Alex. So, thank you.
All right, thank you, Mark. Lots of QR codes here. Just go ahead and hold your phone up and you can go straight to some more resources. We have several of these throughout the presentation, so be on alert. They're going to pull up my slides in a minute, and I'm just going to give you a few little anecdotes about some opportunities that anyone in this room has with NASA science and NASA data. And then we have a series of speakers who are going to tell you more about the James Webb, Roman, and Habitable Worlds Observatory space telescopes, as well as exoplanets and heliophysics, which, if you don't know that word, that means the study of the sun. So, the first thing I want to mention to you is citizen science. Who here in the room knows what citizen science is? Raise your hand. Okay, all right, okay, doing well. I can tell who's awake. So citizen science is an opportunity for anyone to be a scientist, and we truly believe at NASA that anyone can be a scientist if you ask questions and you work with some data. And so NASA Astrophysics and all of NASA science is committed to giving you that data in a way that is free and accessible. We have 29 projects that across all of our science disciplines that give you direct access to NASA data or the opportunity to take data yourself and send it into the NASA archives, the NASA databases. And these collaborations have led to incredible scientific results, over 500 published science papers that have come out of these opportunities. We have them all across the world in multiple languages. And if you just head to our science.nasa.gov site, you can find out about all of these projects and how you can get involved. Many of them are just as simple as using your cell phone. Some of them require a computer, and some of them have the opportunity to go a little bit further if, say, you have a telescope or some other instrumentation. But if you're interested in using NASA data, this is a great entry point into science. If you're a student out there and you can say when you are applying to university that you have done your own research using NASA data, it is going to put you ahead of the pack. And all of this is free and pretty easy to use, which is exactly why we have this whole citizens science program, is to make sure that you can use the data, figure out how to use it, analyze it, and potentially publish a scientific paper. In fact, I just found out this morning, true story, that last year there was a paper in Nature magazine that was co-authored by a citizen scientist, as well as 2 of our NASA scientists. So really, really interesting results, great things that come out of here. And again, very low-hanging fruit. If you're interested in getting into science, many students ask me how to get into science. This is it. To highlight a few of those programs, one is called Are We Alone in the Universe? If you've seen the movie Contact, I'm dating myself, but if you've seen the movie Contact with Jodie Foster, she is sitting listening to radio signals from outer space. That is what this project does. You can do that too, and you can find your own signals potentially. And then we have Exoplanet Watch, where if you have a telescope, you can join in hundreds of people taking their own exoplanet observations. If you don't have a telescope, I don't own my own telescope, you can use NASA data to analyze exoplanet data. And specifically, one of those exoplanet observatories that provides data is called TESS, which Dr. Clampin spoke about, and we have a specific program that is looking at the TESS data. The TESS data has looked at the entire sky, the celestial sky, north and south, and taken a lot of data of trying to find transiting exoplanets by looking for dips in the starlight. And it's too much data for the scientists to go through. So if you want to, you can go online, go to Planet Hunters TESS, get TESS data and look through it and potentially find your own exoplanet. So if you want to make a discovery this year, go online and find this project, and I bet you can. Technology. And now it's going to go like 10 slides. Watch. Okay, and then another really great opportunity is the NASA Space Apps Challenge. This is a yearly challenge that NASA holds across all of our science, as well as our other directorates that are in space technology and human spaceflight. Every year we have a challenge. It is participated in internationally. I think it's over 100 countries participate each year, including South Africa. And it's a really great way for anyone, not just scientists, to get involved with NASA. You go online, you form a team, and then you are given, basically there's a weekend that is a hackathon to work on finding a solution to a NASA proposed problem. And in fact, there is a local team, there's a local group out of the Kirstenbosch National Botanical Gardens that is already, the woman, Nancy Job, is already organizing a team and maybe multiple teams to partake in space apps. So, you don't even have to form your own team. You can reach out and join an existing Cape Town team right here in your backyard, which is wonderful. There's more information. Her contact is here. I'll give you a second to take a picture if you're interested. And then that program is happening, the hackathon weekend is early October every year. So again, if you're interested, here's a QR code, easy for you, take a picture, and you can join a local event, and there's lots of different problems to solve. Again, that's early October, but you'll notice on the slide, if you're interested to form a team, that has to be done within the next couple of weeks. So perfect timing. We also have a couple of other fun things for you to do if you're interested. We have a video game that simulates the Roman Space Telescope, capturing hundreds, if not thousands, of galaxies, black holes, planets. And we also have a beautiful set of exoplanet posters because science is art, and we like to make some art that features our science. So again, QR codes here, take a picture, explore at your leisure later. And then just to finish, I want to talk about the Habitable Worlds Observatory just a little bit more, and you'll hear more about the science towards the end of our program. But this is really the opportunity for the next generation to get involved in science. I had the privilege of being part of the James Webb Space Telescope launch a few years ago, and it's doing incredible science right now. But for the young people out there, this is the telescope of your generation. And there are opportunities to get on the ground now and be a part of the teams that are working on this. So there are already some teams that have, oh, here's a video, wait. So that was just one interpretation of what the telescope would look like. We have not quite figured it out yet, though. It is in the early formulation stages. And again, this is the time to get involved. So if you want to be a scientist, if you want to be an astronomer, you can access NASA data today, start learning, start exploring, start discovering, and you potentially can be leading the charge in 15 years to bring the next great NASA observatory out into space. So with that, I'll leave you with this QR code, and we have, I'd like to give a round of applause for our next speaker, Tom Green. The speakers are going to introduce themselves from here on out, so we don't have as much interruption, but please enjoy. And yeah, thank you.
Thank you, Alex. I'm happy to be here to tell you about the James Webb Space Telescope. Unfortunately, the person who's really been put tons of effort into the James Webb Space Telescope is Eric Smith. He's the program scientist at NASA headquarters. Couldn't make it here due to travel problems. But I started working on Webb in 1997, and I met Eric then. He was already working on it, and I'm very happy to give you a little bit of story of its history and what it's doing now. So, as Mark Clampin told us all earlier, the Hubble Space Telescope was used to look at this deep field in space in the 1990s, and it was pretty clear that we were not seeing the beginnings of the universe, the beginnings of galaxies. Things were already pretty well formed, and there was a big motivation for a new space telescope that was bigger and more sensitive, and going into the infrared because of the redshift of these galaxies to look for the very first objects, the very first systems of stars that formed in the universe. Also, we realized we wanted to see how they evolved through time, how stars and planets were formed, and also to study eventually exoplanets and origins of life and planets in our solar system. We didn't really know that we could study exoplanets with Webb when we were hashing out the science around the year 2000, but it was a versatile enough observatory we could do that. So it really took a very technically challenging observatory, as Mark also alluded to make these discoveries. So it had to be big. It's 6.5 meters in diameter. It had to fit on a rocket. That's too big for the rockets of today's age, so it had to fold up. And it had to be lightweight, because the rockets only have so much capability. I mean, a ground-based telescope of this size could easily weigh 100 tons. Keck is a little bigger, it weighs 270. This weighs 6.5 tons, including fuel. So it was quite a challenge, and also, as Mark said, it has to operate at 40 Kelvin. We had to make it at room temperature and then test it at 40 Kelvin to make sure that the mirrors are well aligned to give us perfect images. So these are some pictures of the telescope itself being put together onto the observatory with the sunshade there. Here are just some other pictures showing some of the 50 or so deployments that it needed to make to unfold after it was launched. This shows how the mirror was attached to its backplane. All of the 18 segments, they're all adjustable in tip and tilt and also shape, even radius of curvature. Here's the thermal diagram. Again, it's very complicated because this side of the observatory is hotter than room temperature from being heated by the sun. This side is 10 times colder. You know, it's only 30 or 40 Kelvin. So, and we tested it in a huge cold chamber at the Johnson Space Center. It was the same chamber used to test the Apollo missions. This video is going to play, hopefully, and here we go. This is a short video showing the assembly of the rocket and putting the James Webb Space Telescope on top and its launch. So this mission was, NASA led this mission. Partners were the European Space Agency and also the Canadian Space Agency. One of the big contributions of the European Space Agency was the Ariane rocket, the Ariane 5 launch vehicle. And that's what it's being put onto right now. So that is the whole telescope folded up. We'd only seen it before unfolded. So this is all real. And it launched from Kourou, French Guiana, on December 25th, 2021.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
These are some of the last images we have of it going away. And that's the solar panel deploying. So we knew then that it was going to get power.
So the James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
So the European Space Agency normally doesn't have a camera in its second stage, but they felt that this launch was important enough to have that camera, and it was a really precision insertion into orbit, enough so that they very much conserve fuel, and we should have enough fuel for 20 years of operations. It was a large undertaking by thousands of people. The number actually grew quite a bit after the successful launch. I found that interesting. But 14 countries contributed to the development of the observatory before launch, and the whole world is using it. So, did it work? Well, we probably wouldn't be here talking about it so much if it didn't, and you've seen a lot of results. There are results being presented every day at this conference, every day outside of this conference, that are really changing our perception of astronomy in these 4 key areas I mentioned and other ones. This is one showing a spectrum of an exoplanet. This is a recent paper. I think it just came out in July. So not only can we take the spectrum of an exoplanet, we take the light and disperse it into its constituent colors. So this is all in infrared wavelengths. This is about 5 times or so redder than what the eye can see. The eye can see wavelengths only down there. But this is where there are strong features due to carbon dioxide, water, sulfur dioxide, etc. And not only can we get the constituents of the atmosphere of an exoplanet, we can tell the difference between the morning side and the evening side, because the evening side is hotter, and the morning side is colder and cloudier. And there have been a few of these papers now produced. So it's really exceeding expectations. This is looking at a star formation region in Serpens. This is a dark cloud. All these little dots here are protostars. They're stars similar to the sun, but they're much younger. They're forming. Some of these have yet to accumulate even the majority of their final mass. And one of the things that you notice here is that there's this predominant shape of these jets coming out. And that means the whole cloud was aligned and the whole cloud collapsed in these directions. And while it was rotating, and they're shooting out jets all aligned. So something that had been predicted before, but not seen on this scale. And we also are studying individual objects in this cloud and how the central objects drive the stars. Before Webb launched, there were less than 10 known high redshift supernovae. These are very important things for understanding the dark energy of the universe, which you'll hear more about in the presentation on the Roman Space Telescope. This JADES image is a deep field, guaranteed time, has 80. So there are already 10 times more known at these high redshifts. So this is probing objects that are as young as 2 or 3 billion years old in the universe. And these are key for understanding how the acceleration of the expansion of the universe has changed over time. The Hubble Space Telescope knew that this little arc existed. This is a very strange structures you hear. They're elongated because their images have been distorted, not by lenses in the telescope, but by massive galaxy clusters between us and these very distant objects. The Hubble knew that these are very young clusters, but it didn't have the resolution to separate these. And Webb has been able to actually separate them spatially and take spectra. So this is like one of the smallest structures ever found in the universe. These are star clusters at a redshift of 10. And so these are subcomponents of galaxies. And by taking the spectra, we measure their age to only something like 500 million years after the Big Bang. This is one of the most distant objects, I think perhaps the most distant one ever found. It's a galaxy at a redshift of 14. It was, redshift was suspected, again, just from Webb with the camera, and it was confirmed with the spectrograph. And this break here is actually in the ultraviolet. It's way at shorter wavelengths in the rest wavelengths of the galaxy, but it's been shifted in wavelength by the expansion of the universe by a factor of over 14, by a factor of 15. So I'll just end here on, this is where, this image, as Mark showed earlier, is the penguin in the egg. It was released as an image chronicling Webb's 2-year anniversary. And I hope you're interested. Come by the NASA booth if you want to know more about Webb. There are many resources online. Just use Google. And thank you for coming.
Good evening. My name is Anjali Tripathi. I have the privilege of also working at NASA. It's a very humbling place to work because you hear about astronauts. Sometimes you even study for PhD qualifying exams with them. So you'll see on the screen my friend here, Chris Williams, who in addition to being a radio astronomer, he went into medicine after his PhD in astrophysics, so anything is possible, and he's now an astronaut. So that's his parking in Houston. If you want to know how to get good parking at NASA, become an astronaut. So I mentioned Chris, though, because I think it's really easy to think about inspiration when it comes to NASA. By a show of hands, how many of you get excited or inspired when you think about NASA? How many of you don't? I appreciate the lack of honesty or the fact that everyone is inspired, because part of our mission at NASA is to inspire the world through discovery. And you've heard the term exoplanets a few times today. So I am NASA's exoplanet ambassador. And what I do is bring the science of exoplanets, which is this field that did not exist when Chris or I was born. And it's something where these worlds we haven't yet seen up close, and so the best we can do for now is visualize them through art. And so on the left, you'll see part of our poster about being on a planet that goes around 2 stars. So imagine having 2 sunsets and 2 sunrises every day. I hope those people who didn't stand up for or raise their hand for not being inspired might have a moment of pause here, because when America became a country, it was not known about any planets other than what had been found throughout antiquity. So for all of human existence until 1781, we knew about Mercury, Venus, Earth, Mars, Jupiter, and Saturn. But when you think about these planets today, you don't just think about stars in the sky that move in different patterns. You have these really visual imagers, right? You might even imagine a selfie being taken by a robot on Mars. All of these are real NASA satellite images. These have all come within the last 100 years, some of them within the last couple of years. It's remarkable, right? It's beautiful. And this is something that I wish I could see throughout the universe. And just to pause for a moment and say, on the far right, what you're seeing are the rings of Saturn actually waving and moving because of the moon Daphnis, right? That's what you see at that top there. Next to it is, and so that was done by the Cassini-Huygens mission, which is a partnership with ESA. At NASA, we have lots of partnerships and collaborations, whether with entire nations or with individual collaborators and universities and students. So this happens at all levels. Next to it, we have the Juno mission, which looks almost like a Van Gogh painting, looking at vortices on Jupiter. In the middle, you see a rover, right, a Mars rover, Perseverance, and a helicopter, Ingenuity, on the left, which is the first time we've flown something on another planet. And next to that is Venus, which has hazy clouds that we would love to go back and see more clearly. But this is an older picture from the Magellan and Pioneer missions. And on the far left is the Mercury mission, which went, the Messenger mission, which went to Mercury. So I mentioned these 5 planets because, again, it's only very recently that we've found other planets. Uranus came in 1781, and then we found Neptune. We won't go into Pluto because this is the IAU, and that's a very touchy subject. For those of you who don't know, the International Astronomical Astronomical Union changed the definition of a planet so that Pluto was demoted to dwarf planet status, but just fun fact, in between the discovery of Uranus and Neptune, Ceres was found and it was named a planet. Then it got demoted to an asteroid. Then it became a dwarf planet again. So dwarf planets can make for good stories either way. But I show you this picture of the night sky because if you actually look closely with a space telescope, specifically the Kepler Space Telescope, in that one patch of the sky near the constellation Cygnus, you'll see all of these colored dots representing planets that we've discovered. So as of this week, we know of 5,741 exoplanets. So you keep hearing that term exoplanets. Exoplanets are planets that orbit stars outside of the solar system. So all of the stars that you're seeing at night are actually host to their own worlds. So this is a view from a program called Eyes on Exoplanets. You can go and access it on your web browser, but it actually shows you what the sky here in Cape Town looks like tonight. So you could go out and look at Cygnus, you could even look up at a patch of sky, and Eyes on Exoplanets will even show you where telescopes like the James Webb Space Telescope is right now, or TESS, or anything else. And you can see where naked eye stars. So I encourage you to go out tonight and look for the stars that host planets, because it's not just the stars, right? Even though that's what we see and that's what we detect to find changes in to find planets, but to say, I know that there's a planet out there, and I wonder what they can see out there. So when we talk about exoplanet discovery, we talk about NASA missions, and you might think, oh, I have to have a space telescope. But actually, they get discovered from telescopes and observatories all across the world, big and small in space on the ground. Here in South Africa alone, by my estimate, at least 46 exoplanets have been discovered, some using the KELT and WASP facilities. So again, you can go and explore this on Eyes on Exoplanets and see what has been discovered near you. And just like Alex mentioned, there's the Exoplanet Watch program where you can be a citizen scientist and use robotic telescope data from the Micro Observatory to help us do a better job of understanding these planets. And I want to put a sonification out here for you, because when we think about the universe, it's easy to just think about what you see, but I want you to listen to what we've seen and found in the stars. And you can see how we found them with the different colors of the dots. That's the technique for discovering these exoplanets. So get ready for what the Kepler mission finds. And I would say that for those of you who are looking for ways to do more accessible outreach or incorporate it into your work, we have lots of sonifications and other resources, so I encourage you to check that out. But I love this because you get a sense of how just one telescope staring at one patch of the sky for longer and longer found planets, just like we talked about the ultra deep field and what you can find if only you had the facility to look more. So you saw, though, that a lot of these planets, thousands of them, have actually been discovered with what you see here in that sort of bluish colored transits. So what is a transit? So in April, we had the solar eclipse passing through North America. That was very exciting. I was very fortunate to go to Texas and see this. And I think we all know that an eclipse is when it can be a total solar eclipse and it becomes nighttime during the day, right? The moon will block out the sun. So that's what you see, that black part of the sun missing is the moon's shadow. But what you can sort of see there, that little dot, that's actually the International Space Station flying between us and the sun. So that's its shadow. And we say that's the transit of the International Space Station, because whenever something small is blocking out the light of its star, we call that a transit. And so this is the technique that Kepler spacecraft that I mentioned, as well as TESS, where TESS stands for Transiting Exoplanet Survey Satellite. So whereas Kepler looked for most of its career at one patch of the sky, TESS is actually looking all across the sky to find planets. And so you might say, how does this work? How do we find planets that have the right geometry? And the answer is by looking at the light and measuring how it changes over time. Because if you see the light blinking in a particular pattern, it might mean that it's getting darker from the planets going around it. And if the planets keep passing around it regularly, you can say, oh, that's a planet, not just something, driving by between me and the star. And so this is something that we've actually been able to use to discover all kinds of amazing systems. One of them that we're really excited about in the exoplanet community is the TRAPPIST-1 system. So this is a relatively nearby star, right? You'll see it's about 40 light years away. It's smaller than the sun. It's a red dwarf. But you can see that every time planets pass in front of the star, we see these dips in our data. So what you see, all of those dots are showing you the light and how bright it is over time. And so you can keep seeing, right, like the B keeps coming back on the shortest period, and that means that's a planet that's really close to the star. So it's, you know, you'd have birthdays all the time there. Whereas if you were further out, it would take a lot longer and there would be fewer presents. And so again, thinking about art and how we translate this data, we're discovering these planets without ever actually seeing them, right? We're finding these dips in the light. And so we actually worked with our artists. One of the lovely parts about working at NASA in California is we get some ex-Disney artists. So Joby, who did this, used to work for Disney. So if you want to work at NASA, it's not just being an astronomer. There are many ways to come and join us. And they imagined being on one of these planets, TRAPPIST-1e, which is sort of one of the middle ones in the 7, where when you looked up in the night sky, you wouldn't just see a star or a moon, you would actually see the other planets that are so close to you. They would be in the sky. So as of right now, I mentioned the nearly 6,000 planets that we've found. What have we found? Some of the planets look like what we have in the solar system. There are some gas giants like Jupiter. Sometimes they're very close to their star or not as far out as Jupiter. There are some planets that are like Neptune. Some are smaller. We're very creative. We come up with the name mini Neptunes. We find planets that aren't anything like what we see in the solar system, and we call those super Earths because they're bigger than Earth but smaller than Neptune. Again, very creative. But what you can see is in that pie chart, only 4% of the planets that we've discovered to date, about 200 of them, are about the size of Earth. And of those 200 planets, only 44 of them are in the habitable zone. So if you haven't heard of the term habitable zone before, let me just share what that is. So on the left, you can see a diagram comparing the solar system, which is on the bottom, to TRAPPIST-1. And so since we go around the sun, if we were really close to the sun, it would be a lot hotter, a lot more sunburns, and water would turn to steam more easily. Whereas if we were very far out, right, at the distance of, say, Pluto, it would be really cold and icy, right? And I like drinking water quite a lot, so I can say that for me, that's absolutely essential to life. And when we're studying life in the universe, we want to go after what we know. So by starting out our search for life for places where liquid water is possible and there's an atmosphere that supports that, we say that that's the habitable zone. So that's what's shown in green. And you can see that the habitable zone around the star TRAPPIST-1 happens to overlap with multiple planets there, and those are all about the size of Earth. So it's fascinating to study the system because if we want to find life, find alien life out there, we first need to see where it could be. So find an exoplanet, okay, we've done that lots of times, and look, are there the conditions for life? Could there be liquid water? So are there planets in the habitable zone? And then we actually want to look for life itself. But this is a really helpful concept, and so that's why you keep hearing about the Habitable Worlds Observatory, as our Valentine's Day comic here says, right? You had me at habitable because it's such a rare thing that we're searching for. So one of the amazing techniques, though, that we can use to study planets isn't just to find them when they transit, but to actually look at their atmospheres. So the James Webb Space Telescope has this ability. We can also do this with other facilities, but Webb is amazing because it can take the light from the star, it can disperse them through almost a prism, we call this spectroscopy, and compare that to when the planet is in front of the star. And by looking at the signature of the planet's atmosphere and taking out that of the star, what we're left is, when we subtract that, is what's in the planet's atmosphere. And so this allows us to get a sense of what are the chemical elements, what are the molecules there from this planet that we can't see with our eyes and we can only detect from the starlight, which is just incredible. And we've made all kinds of discoveries. So all of this may not look that exciting, right? It's just a squiggly line, but imagine being able to sense carbon dioxide so far away that, you know, you can't see it, but the James Webb Space Telescope can, as well as so many other molecules that we haven't seen before. So this is a composite of a planet that's kind of like Saturn. It's much closer to its star, so we'd say it's hot. But one thing that's kind of remarkable in that lower left figure is it's showing you the spectrum, right, the amount of light that we're getting when we put it through our prism, showing sulfur dioxide, which is kind of like a pollutant. It's like ozone. It's something you can only get when ultraviolet light is reacting with the chemistry in your atmosphere. So we can say things are happening in this atmosphere, and we can actually detect this using our telescopes. So there are many beautiful things that James Webb can do for exoplanets, but most of them aren't the beautiful pictures of penguins and eggs that the universe produces for us in the form of galaxies. With exoplanets, we have to use our imagination. So two of the big discoveries recently, one of them actually comes from Tom, who just spoke to you, and his team, which is, as we're looking for TRAPPIST-1 and trying to see, is there actually water and atmospheres that could support this? What happens if we look at it with Webb? He actually found with his team that the closest in planet, the closest in couple, are actually so barren balls of rock that there is no atmosphere there. So there's probably no hope for life on those, but we're still studying what else is there. And another one, and we have this beautiful poster of a world where we say skies sparkle from above a never-ending ocean of lava. We originally thought it might rain diamonds and rubies on this lava planet. Webb has actually been able to detect an atmosphere around this rocky planet, which is remarkable because you want to be able to say that, yes, my telescope can do that. But unfortunately, Webb has said it probably doesn't rain diamonds and rubies, which is quite sad. But all of these beautiful posters are something that Alex pointed out. You can go to exoplanets.nasa.gov for anything I've shown you today, and you can download it and decorate your walls. So I just want to finish up with a couple of things, which is the Voyager spacecraft. There are two of them. Voyager 1 in 1990 on Valentine's Day looked back at the solar system and took a picture. And that's what you can see flashing up there. All those little pixels are actually entire planets. So you can think about that picture I showed you at the beginning with a selfie of a rover on Mars and all the detail, and now thinking that you're so far zoomed out that all you get is a dot. Well, what we want to do in the future is actually look at exoplanets, right? So this is part of what the Habitable Worlds Observatory will do. It's actually going to try and get to that level of seeing something like Earth. But for now, from the ground, we've been able to use the Keck telescope and look at planets that are big like Jupiter around a young star, HR 8799. And so you can see those 4 planets, B through E, that are circling around it. The star has been blocked out because, again, it's too bright. And so if we want to see the planets, we have to block it out using a coronagraph. And a recent discovery, like hot off the presses in the last couple of weeks, and this is actually a star that you can go out and see from the southern sky here in Cape Town tonight, so I encourage you to do that, which is Epsilon Indi AB, which is around this star. The James Webb Space Telescope was actually able to see a planet like Jupiter, but it's much cooler. This is a star much more like the sun. It's a cage star. It's a little smaller than the sun. But this is remarkable because it's cool and it gives us hope of all of the amazing discoveries we can image. So again, you might say, Anjali, these are not the most exciting, beautiful images. And that's because we're working on getting to those beautiful pictures, right? We didn't have those beautiful pictures of Mars and Mercury 100 years ago, but we're getting there. And so this is why, as Dr. Clampin mentioned, right, 1 million times fainter than the sun gets you an image of a hot Jupiter, kind of like what you see on the far left. But if you can go 10 billion times fainter, then you can start to see something like Earth. And that is so difficult. It's like comparing the amount of light from a lighthouse, not just to a firefly, one single firefly, which is that hot Jupiter, but actually one single bioluminescent algal. So if you look at bioluminescence in the ocean, just imagine one of those organisms. And so this is what the Nancy Grace Roman Space Telescope is going to help test with its technology in its coronagraph instrument. And this is part of what we're doing to explore exoplanets in the future. Because again, when Chris, when many of you in this room were born, we knew about 9 planets, then there were 8, and now we know about 5741, I guess, plus 8 in the solar system. And we know there are hundreds of billions more out there. So you can see how about 75% of these exoplanets were found with transits. At the time I wrote my first science paper in college, most planets were found with the radial velocity method. In the future, Roman is going to find lots of planets with microlensing and imaging, and the Habitable Worlds Observatory will not only find them, but it'll actually tell us, are there signs of life there? So you can see there are lots of ways that we are studying exoplanets, and I hope you'll consider getting involved. I was an intern first at NASA 20 years ago, if you can believe it. I was working on Mars rovers much smaller than what we have today on Spirit and Opportunity. So we have in multiple languages, coloring books. I encourage you to be there and get involved because we really need everyone to join us and inspire. So thank you. And again, go to our website and you can print out a poster like this. Thanks.
Space Telescope, And it's going to allow us to observe the full range between the outer edges of the solar system to the stars in our galaxy, the Milky Way, to other galaxies, and to the distant early universe. So definitely a very exciting mission. So this mission is named after Dr. Nancy Grace Roman. She was the NASA's first chief of astronomy, and she was a role model. Without her advocacy, her championing of doing astronomy with space-based missions, we wouldn't have missions like Hubble or even the Roman Space Telescope. So definitely a driving force in astronomy and a role model. As Mark alluded to, Roman is a flagship mission. It's one of the missions that came out of one of the decadals. This is the 2010 decadal survey. And the main reason for building this spacecraft was because back in the late 1990s, observations from the ground and observations with the Hubble Space Telescope provided information that led scientists to understand that the universe was expanding, not only expanding, but also acceleration of the expansion. So they realized they needed some sort of like facility in the infrared able to obtain very broad images with resolution like Hubble. And this is one of the main reasons to build this telescope, to understand what we yet don't understand, which is what people call dark energy, which represents about 75% of the universe. So definitely Roman is going to create big step forwards into understanding this topic. But while they were doing this decadal survey, they also realized that we could use such a facility to do other kind of things. And this is why they said, okay, we could use such a facility to detect more galaxies, the universe, and to provide observations for other topics in astronomy. So this is why the Roman Space Telescope is going to dedicate 25% of its time to other kind of general astrophysics problems. And also they realized that they needed to both advance the field of exoplanet demographics, as previous presenters alluded to. Kepler and TESS have been very successful at detecting giant planets in very compact systems, so near their stars. But we don't have the capabilities quite yet of detecting also exoplanets in the outer regions. The amount of statistics is rather low, and we realize that through micro-lensing, we can advance the study with Roman. And last but not least, in our pursuit of imaging Earth-like planets, the decadal said, okay, we need to try new technologies that can advance the ways we take images of planets in our universe. So let's talk a little bit about Roman. Roman is, it has two main instruments. One is called the wide field instrument. This is like a huge camera with 300 megapixels. And it also has something we call a technology demonstration, which is called the coronagraph. It also features a 2.4 meter in diameter primary mirror, so a primary mirror similar to the one we have on Hubble. And it's going to be located on the Lagrange 2 point. That's a specific point where also Webb is, which is at 1.5 million kilometers. And last but not least, we're planning to have a baseline mission of 5 years with the goal of having a mission with a total of 10 years, depending on the fuel that is used for the operations. This is a sketch of what the Roman mission looks like. You can see some of the key features here is it has a solar array, which provides power, about like 4,000 watts, which is the power that consumes, let's say, 2 microwave ovens in our houses. It also features this sort of like outer barrel assembly, which in addition to the sun shield, keeps the telescope cool, but also sort of like protects from any unwanted stray light that can get into the primary mirror. In the center, you have something which is called the instrument carrier. This is a sort of structure that holds the two instruments, the wide field instrument and the coronagraph. And at the bottom, you have what we call the spacecraft bus, which also has the avionic panels, and also you can see the high-gain antenna that is going to allow us to transmit all the data we have on the spacecraft. So Roman is managed by NASA's Goddard Space Flight Center in Greenville, Maryland. They're also doing all the integration and testing of the observatory. And they also are providing some other key subsystems, such as the spacecraft and other components for the instrument. But these missions wouldn't be possible without the contribution from different other organizations and even international collaborations, as it happened with Webb. You can see here that some key institutions, such as L3 Harris, is providing the optical telescope assembly. We have BAE Systems in Boulder, Colorado, that has built the wide field instrument. We have the NASA's Jet Propulsion Laboratory working on, they actually built and delivered the coronagraph, and so on and so forth. Here, we're not listing the international contributions, but they're equally significant as well. So just to give you a reference, it takes time to build these missions, as you can see. We usually get to enjoy the images we get from Webb, but it's years of development and the hard work of different scientists and engineers over years. So after the guidance from the decadal, Congress appropriated funds to start formulating the mission. This is what we call the Phase A. This is when engineers and scientists get together and they go to the drawing board, get a design, they have trace studies on power, thermal mass, and so on. And as you can see, that drawing process lasted 4 years. And since February 2020, we started with the implementation phase, which is basically starting with the fabrication of the different elements. As you can see, we're here getting to Phase D. That's going to start in January 2025. This is when the assembly, integration, and testing happens. And some key things to mention here is that, as you can see here, some of the main systems have already been delivered, like the instrument carrier and the coronagraph. And as we speak now, the wide field instrument was delivered yesterday. So fresh off the press, we're very excited about the progress on this mission and looking forward to the steps moving forward. In the next few months, we're going to get the optical telescope assembly, which is actually the telescope. And as I mentioned before, next year, we're going to have the implementation, the integration and testing that is going to last about 1.5 years before we send the completed observatory to Florida for its launch on a Falcon Heavy. After 90 days of what we call commissioning time, it's going to start the operations, gathering all the data sometime in 2027. We're expecting this launch to be before May 2027. So as you can see, it's going to take 11 years from the beginning of the formulation, and we're very excited about it. And I wanted to take you on a journey and show you a little bit some of the progress that's been done for this observatory. This is the centrifuge testing of the instrument carrier at Goddard Space Flight Center. The testing of the high-gain antenna. This is the environmental testing for some of the panels and structures. This is the propulsion system. This is all at Goddard in the high bay. That's the spacecraft bus, and we're integrating the propulsion system into the spacecraft. A lot of hard work by different technicians, engineers, and scientists put into this process. Meanwhile, At BAA system in Boulder, we were experiencing the wide field instrument going into environmental testing. And at L3 Harris in Rochester, we have, here's the telescope. This is a 2.4 meter in diameter primary. We're also in the process of doing some environmental testing and the delivery of some of the solar array systems. So very exciting progress. Of course, we're looking forward to the next steps on this mission. One of the key aspects of Roman is that it's going to provide a quality of images which is similar to that of Hubble. This is the three dust pillar in the Eagle Nebula. And you can see how it compares the field of view from Roman to that of Hubble. You can see, at least in the infrared, it has a field of view that is 200 times bigger than that of Hubble. That's going to make Roman 1,000 times faster than Hubble. So we can do science, we can have a lot of data that is going to help answer some of these questions I was alluding to before. You can see here, compare the size of the mirror from Hubble, Roman, and Webb. You can see their different field of views. You can see, the huge field of view of Roman compared to Webb and Hubble. And here you can see the wavelengths of operations they have. So this is basically the kind of light they looked at. You can see that Hubble is more specialized in the ultraviolet, while Webb is in the near infrared to mid infrared. Roman provides this sweet spot in between. And this is good because we're going to be able to sometimes compare observations that were done with Hubble and like archival data, or with Webb, or we can have some sort of follow-up observations with the most specialized observations, such as the one from Webb. And of course, these big images are going to provide a lot of data. Just for reference, in the 30 years of operations by Hubble, we have obtained 172 terabytes. Just for reference, 1 terabyte is about like 500 hours of movies. Roman is going to provide 20,000 terabytes in the 5 years of operations. And the cool thing about this is that all this data is freely available as soon as it's taken. Most of the data are going to be in the cloud, so scientists are providing very creative solutions to make sure that we provide calibrated data, real-time, quick, and very efficiently. So no doubt that we are sort of like rewriting the way we're going to be doing data analysis in the future. We were talking about exoplanets before, and Anjali talked about Kepler. Look at the position of the planets in our own solar system. This is all the planets we have discovered thus far, the 5,000 plus planets. If we would use Kepler to detect planetary systems like our own, it wouldn't be possible. And through gravitational microlensing, Roman is going to help us bridge that gap. It's going to help us detect planets in configurations like what we have in the solar system. We estimate that Roman is going to detect about 3,000 planets, exoplanets in this yellow area, and it's going to contribute about 100,000 planets using the transit method that were discussed before. So no doubt we're going to really advance the exoplanet demographics. And I talked about the technology demonstration, this coronagraph that was described before. Roman is going to be unique in that we're going to be testing new technology. Even though coronagraphs exist in other missions such as Hubble and Webb, Roman is going to feature adaptive optics in space for the first time. And this is what's going to allow us to create this contrast needed to detect these very dim exoplanets. Mark mentioned that in order to detect Earth-like planets, we need a contrast of about 10 billion times. From the ground, we already have between 100,000 to 1 million. Roman is going to allow us to have a contrast of about 100 million. So still we have some room to go. We need still to lower that or to improve that contrast by a factor of 10 to 100, but this is a stepping stone in our aim to have the Habitable Worlds Observatory and have similar technologies in that future observatory to detect Earth-like planets. So I have discussed at length the great aspects of Roman, their huge images, the huge resolution, and the amazing things that it's gonna do for exoplanet, the discoveries. Some of these is gonna help answer questions that arose from missions such as Hubble, TESS, and Kepler, but it's also gonna help answer the key questions that we heard about at the beginning. How did the universe evolve? Are we alone? Or is Earth the only habitable planet? So Roman was built to help answer those questions. And again, we're really excited about it. And I hope that you also are looking forward to these observations. So please get involved. And if you want more information, there's the QR code. Thank you so much for having us here. It's been a pleasure.
Hello, I'm Tom Green again. I had so much fun working on the Webb Space Telescope that I decided to work on habitable worlds also. And as Dr. Clampin said, this is going to be a generational effort. So we need a lot of young people to get involved in this, and I'm happy to see already there's a great initial response. Also, Dr. Clampin showed that what NASA does in these big missions is not just a guess or somebody's wild idea, but is pretty carefully considered and deliberated by the National Academy of Sciences. And who are they to decide? Well, they get the whole US community together. There's often also a substantial international participation in deciding what the US should be doing. So the 2020 decadal report, which came out later, as Dr. Clampin also said, was recommended this a next flagship observatory that could see in the visible and near-infrared light to study the universe at short wavelengths and particularly be able to image Earth-like planets around sun-like stars. So what would we expect life to look like? What would, and would we recognize it if we saw it? I guess that every time we've assumed that we knew what something was in the universe, the big issues, often we've been wrong. We first assumed that everything rotated around the Earth, right? The sun revolved around the Earth, all the planets around the Earth. But it was eventually figured out that Copernicus helped figure that out. No, it wasn't that way. And so we want to be able to make sure that we're not biasing ourselves with our own preconceptions of life, and we don't miss out on what other forms of life may be. One great illustration of this is looking at how life on Earth probably evolved over time, even on the same planet. So this is what this shows in the Astro 2020 picture. It showed how there are different epochs of life on the Earth. Modern Earth was different. I'll get into that a little more later. Also, this decadal survey was focused on looking at transient events, and those are going to be found by like the Roman Space Telescope and some ground-based telescopes like Rubin, and they will give a lot of keys to high-energy explosions in the early universe. And also, we need to know more about how galaxies evolve. So Webb is showing us the earliest galaxies, but a lot of light is being missed from the ultraviolet, where a lot of their young stars are very bright, and it's important to have an ultraviolet and visible light telescope. So These themes come together in the Habitable World Observatory, looking for this life in the universe around exoplanets, and also looking for how galaxies evolve and grow. Ultimately, we would like to get a picture like this, as Dr. Clampin and I believe Anjali also showed here. This is going to take a lot of effort. Anjali showed how much we can learn with the transit technique, but we're just not going to be able to use the transit technique to be able to search Earth-like planets around Sun-like stars and look at their atmospheres and see if they are either conducive for life or whether they show indications of life. This is that picture again, showing what life looked like on Earth at different times. Here we have the modern Earth, which is only in the last 10% of the age of the solar system. Only in the last 500 million years have we had multi-celled plants and animals, where free oxygen has become common, and so we can recognize that in the spectrum of the Earth. We've done all sorts of simulations. We can do this by looking at moonshine, the kind that actually comes from light from the moon, not what is made in certain parts of America. Another epoch of life on the Earth, here the Proterozoic epoch, was more complex single-celled organisms. Oxygen was starting to come up, and you can see this is a tracer of oxygen, this ozone here. It's the oxygen we breathe is actually O2. It's two oxygen atoms put together in a molecule. But what had to happen first is that you needed photosynthesis, which is happening here, to create oxygen, and some of the O2 molecules will collect another oxygen atom and become this ozone, this O3. Also, what also happened is the Earth's mantle and the Earth's surface had to evolve. There was a lot of iron, and we had to get oxidized, and also under the ocean. So that was an important thing before free oxygen could accumulate in the atmosphere of Earth. And finally, what we believe is one of the earliest phases of life on the Earth, before which Earth was really unhospitable for life, was there were these methanogens, these very simple bacteria, again, single cells, but much simpler than the multi-component cells in the Proterozoic. Here, these very simple life forms would feast on methane and also could produce oxygen, but take CO2 in the Earth's atmosphere that was outgassed by volcanoes and whatnot, and convert some oxygen. But again, as I mentioned earlier, this free oxygen had to was getting absorbed by iron and other elements on Earth, I believe also sulfur. So we want to make an observatory that can see all of that. And that's going to take some capability. I'll just go back here and show that these different epochs have very different spectra. And this is just taking the light from the planet Earth and dispersing it into component wavelengths. So this modern Earth looks much different from the Archean Earth, and we need to have the capability of seeing all this and more. We're actually looking at another kind of life, which don't ask me about because I'm not an expert in this. So we're looking at sort of 4 possible life scenarios in our very early explorations of habitable worlds. Also, I mentioned we want to be able to understand galaxy growth. This is a Hubble image in visible light, and this is a simulation of habitable worlds being able to look at a low-mass galaxy. Again, we want to see how the first objects we discovered with Webb evolved into modern structures like the Milky Way we have today. So what kind of telescope and instruments are going to do this? We don't know. We have a vision, and we're starting to flesh out that vision. So the techniques that we're doing is that we want to look at a first round of mission architectures. And this is to just explore possibilities here. I'll show you some pictures there. And then look at feasibility, see where the technology needs to be advanced in order to perhaps achieve these architectures, and then figure out, are they going to fit on existing rockets and rockets planned for 20 years from now, and work with the vendors to make sure we have something that could deliver this. because we want something big and it's going to be fragile. So we realize right now, we're very early in the process, nothing that we think of now is actually going to launch, but it can inform what will launch. So we're just really fleshing out the vision. And to give an example, here is an image of one of the first designs. There was a book in 1997 that came out, Concepts for the James Webb Space Telescope. You saw the pictures of it. It looks pretty different in reality. And this is what it is like now. And just like the first concepts we have for habitable worlds now are going to evolve considerably by the time it launches. So we're looking at 3 different observatory architectures in this current phase. This current phase is lasting about 2 years of exploration. The first architecture is very much like James Webb because we know we can build that, except we need to control the mirrors 1,000 times more precisely than we do with Webb. So that's a tough problem. It'll be a little easier because they don't have to be cold, but it's still very much a tough problem. So that is this one. I'll show you some more pictures in the next slide. Also, you notice that the secondary mirror, which focuses the light on the instruments, is off to the side here because that is better for doing high contrast images of solar systems. This is another concept. It's similar to the first one, except the mirror is round. It doesn't have these ragged edges from the segments. Again, that makes things easier for the coronagraph, which has to sort of snuff out the starlight. And finally, this is one that's on axis like Webb, but a little bigger in diameter. So it won't have as high contrast, but the bigger diameter could help. And this shows these different architectures, how they could fit into fairing. So this first one folds up like Webb and has this mirror cantilevered out. This is the one with the round keystone segments. They're not hexagons. And this is the one with the keystone segments and the on-axis mirror folded up. So we don't just need a telescope. We need an instrument also. So the instrument you've been hearing about, this coronagraph, is going to take those high contrast images of those solar systems, hopefully find other planetary systems, terrestrial planets like Earth. And as we've heard also from Anjali, Dr. Clampin, and also Lucas, that it has to suppress the light by a factor of 10 billion. So it's not an easy task. It has to look over a large range of wavelengths to be able to look at all those life indicators that I showed. Also need a wide field camera so we can study galaxy evolution. We can study other ultraviolet processes in the universe, high energy processes. And finally, we need a spectrograph that will take the light that we see in the camera and be able to disperse it. So we can actually see what spectral lines are there, what radiation is present, what atoms are present. So this is just the beginning. And I encourage all of you to look online for more information. Again, come by the NASA booth. We have some flyers. There is a mailing list. You can take a picture. I've got a few more QR codes here. There's a website to get involved. There are over a dozen working groups, or dozens of working groups, looking at different aspects of the habitable world science and technology now. These are going to get rearranged some around the end of the year. And we have also a community Slack space where you can ask questions and get them answered by experts about what is going on. And again, we really need everybody's help on this. This is a hard problem. It's going to take a long time. And everybody has a contribution to make if you're interested, and we welcome that. Thank you.
Hello, everyone. I'm Arina Kitiashvili from NASA Ames Research Center. And actually, my career as scientist started from actually, I'm trained astronomer. And at some point, I changed my field to heliophysics. And during this presentation, I actually want to discuss about heliophysics and share my excitement. And I hope everyone finds some special spot in heliophysics. And the sun actually is so special star. It is most important star in our life. And for obvious reason, we are all depend from this. But not just this, it is star which actually join everybody. It doesn't matter background, our personal interests, goals, even cultures. If you look in your nationality, history, I'm sure everybody find example when in culture sun reflected in different ways. But in addition to this, I want to say sun actually inspire each of us. We can just see outside of our window and see a very beautiful day and be happy. Sometimes we see a very exciting thing, probably you watch news and see very different stuff. And I'm going to share some of them. And one important key point, because sun and heliophysics itself very inclusive. What I mean by this, it is not about our background or kind of personal opinions, because it joins very different fields. And actually, you can do heliophysics even if you never done this, even if you don't have major in physics. But because sun, it is, can be considered as art object, it can be considered like science object, and actually we have connections between different fields and just we can enjoy even nice pictures and movies. And on slide you see just heliophysics overreaching goals. And you see it is not just discussion about like sun as object, but also sun considered in heliophysics also as part of environment. And one of most important thing about it, because of technology, we also depend from solar activity. And it is a huge topic in heliophysics, how to understand how sun operates. At different scales, it can be like decade scales, we call this solar cycle variability, or it can be short time scales, like eruptive activity. And and because sun is so important star, we investigated with very different instruments. But not just, again, sun itself, but also environment. And in particular, we have a lot of space missions which study how Earth environment or other planetary environment change and interact with solar wind, for instance. And also how we can get more information about it. And I want, because so many missions, I want to mention just a few of them. And you see, for instance, missions like SDO, SOHA, and STEREO, they observe whole sun. But STEREO mission is special because for some time we was able to observe far side of the sun. And it is pretty amazing because it was so unique opportunity when we see both sides of the sun. But if you want to look really on the sun with really great details, we should take data from Hinode and IRIS. And actually, these missions allow us to observe sun with great detail at different layers of atmosphere and corona. Other missions like Parker Solar Probe and Solar Orbiter actually intend to investigate details of origin of solar wind and answer a very simple question, why corona is hot? And it is a big question in heliophysics because we know temperature at the solar photosphere is roughly 6400 Kelvin. it decreases with height, and suddenly, as we pass transition zone, temperature going to million degrees plasma. And nobody can answer this. We have many theories and try to find a way why it is. And it is one of reasons why we actually have future missions. It is actually more than this, but I just identified 3 of them. And the intent actually answer question, like why corona is hot, what is origin of solar wind, and actually how on a local scales corona looks like. And because it is so many data, and we observe sun for many years, we actually have huge amount of data. And what is most impressive for me, what we can get actually information about sun below surface at different scales. For instance, we can actually know how sun looks like below visible surface, but not just how it looks like, we know how it varies with time on different scales. And on this slide, for instance, you see how flows, just structural flows on very large scales at some moment of time. But we also can detect in advance emergence of new sunspots or active regions. And we develop now technology how to predict it. And it is critical because we want to know how space weather will be in next few days. And also, we have observations from photosphere of the sun to near-Earth environment. And I just want to mention, it is so huge amount of data. Actually, just one instrument from Solar Dynamics Observatory, instrument called like Heliosysmic and Magnetic Imager, produce every day 4 terabyte data ready for use. And this space mission already operates for 14 years. And you can imagine how much data we have just from single instrument. And what is most amazing, we actually can use this data anytime. And everyone can get data. If you don't feel what you don't have skills, you can just go to HelioViewer, for instance, find interesting spot for you with the most interesting observations, and make a movie and just enjoy. But if you really love it, you actually can get specific data what you selected. And sun actually extremely well-studied star from one point of view. And now I want to discuss, because we have not just significant progress in observation from observational side. We also do a lot modeling on different scales. We can do modeling of sun on global scales, but also on local scale. And I decided to choose just a single example for very quiet sun region, so it sounds boring, and I want to show you how it looks like. Actually, these simulations we call like realistic type simulations, and you see turbulent flows near surface and low layers of solar atmosphere. And colors show actually turbulent flows strongly twisted, and the red colors, it is more twisted flows. And even you can imagine, even if you consider just very quiet sun, very quiet, we still have many eruptions. But what happens when we have magnetic fields? We start to see really significant eruptions, and physics, of course, getting more complicated, and most exciting. But advantage of such approach, we actually can model observations from space missions and understand better what we're actually observing and test our ideas. But our experience actually can go beyond of the sun, and such type simulations can be extended to model other stars. And for instance, this example of planet host star, solar type star, and for first time we actually can see how stellar surface looks like. I don't know when it will be actually observed in such high degree of detail. But what is important, it provides us kind of ground truth to test our ideas and test our understanding actual observations. And what is most important, we have now Heliophysics big year. And actually it is extremely exciting because it is now, this year is very special for different reasons. And this year starts from annual eclipse in October 2023. And this year, just in April, we had totality. So many people was able to observe a total solar eclipse, which quite amazing. And I know many citizen scientists built own telescopes to observe it. And the uniqueness of this totality was it crossed whole Northern America it crossed several countries, and many people was able to observe it. And but I want to say right now we are in solar maximum. What it means for us, it is most exciting time to observe the sun. And I want first mention few days in May when we had major solar storms. And actually, many people around the globe was able to see northern lights. Even in Greece, it was kind of very surprising. I'm from California and was able to see it. I never see this before, actually. But sun actually still active. And you see actually even during last couple months, we had major eruptions. And I took such observations from GOES and just for last week. And you see strong spikes in X-ray flux. It actually reflects some eruptive activity on the sun. And you see just within 1 week how many eruptions we have. But Heliophysics big year not finished yet, and we expect, in addition to solar activity, we expect actually major event. And we're going to observe event like closest approach to the sun with Parker Solar Probe. Never any spacecraft was not able to get such close to the sun, take observations from local environment, locally, and also observe solar surface and atmosphere. And to finalize, I want to say Heliophysics today is synergy of technological, theoretical modeling, and many advantages. And actually, I want to invite everybody, try to look data and find what you are interested in this. Because it is now most exciting field in the world. And if you are interested in this, please go to Google and you can just find a HelioViewer, for instance, and explore amazing amount of data. And welcome to Heliophysics big year. Thank you.
All right, let's give another round of applause for all of our speakers. I hope you all enjoyed learning about NASA Astrophysics, NASA Heliophysics, all the exciting research that you can take part in from even your home. We have one small presentation left, so I'd like to invite Dr. Clampin and Dr. Schmidt up to the stage, as well as representatives from the African Astronomical Society.
Good evening. My name is Greg Schmidt. I'm director of NASA's Survey Institute. I want to start by saying how happy I am to be here, more so than perhaps some. It took me a full 4 days to come from California, and as I pointed out to my wife, that's longer than it took for the astronauts to go from Earth to the moon. We study the moon with my institute. We study all aspects of it. I enjoyed all of the presentations, and just to resonate with the last one, my institute was actually the very first one to stream the eclipse when it hit land at Mazatlan. So if you happen to be watching it, then you were seeing our stream, which I'm very proud of. The moon, it's not our, like I like to say, it's not our grandfathers and grandmothers' moon. It's so much different, so much richer, so much more interesting. We've learned about water on the moon. There's a vast amount of it, and other resources that are going to make going to the moon, again, very, very different than it was back in the 1960s. NASA has its Artemis program. Artemis 1 launched successfully over a year ago. Artemis 2 is going up next year. Artemis 1 was without crew, but Artemis 2 does have crew. I like to think of it as, for those that might remember, as very similar to the Apollo 8 mission that was in Christmas of 1968. Just a very influential one for me as a kid. And then Artemis 3 is the first landing on the moon with people in over 50 years. And so it's a really big deal. But we're doing it differently now. We're going for a permanent presence on the moon. We're also doing it internationally. Whereas in the 1960s, it was just the United States and the Soviet Union that were competing to get to the moon. We work with countries around the world now. My institute alone has 12 international partnerships with 500 or so scientists around the world. We're building a partnership with our friends at the African Astronomical Society, which I'm just incredibly excited about. And so that's one key aspect. Another key aspect is commercial. There's, we are doing this with new companies that are going to the moon for profit. And so that offers some really exciting possibilities in terms of lowering the costs. And also for all the younger people in the audience, all the school kids and everything here, and I know that there are a number of them. How many kids are school kids? Yay. I am just so glad to have you here. You're going to see a really different world, especially when we think about space, than we do, certainly than we did when I was a kid, but even today, the opportunities are going to be absolutely amazing. With the commercial, we have something called the Commercial Lunar Payload Services program, but I'm going to talk about that a little bit more in just a minute because it has to do with what I'm going to be giving the African Astronomical Society. We have more data on the moon than any other body in the solar system, and this is because largely of the Lunar Reconnaissance Orbiter that's been in orbit around the moon over 15 years now. And so bringing the moon to everyone is part of our mission, both at my institute and elsewhere within NASA. One thing I want to point out, and for those who are going to be in my session on Monday, you'll find out more about this. We have something called the International Observe the Moon Night, where we invite people around the world to join us in looking at the moon through telescopes set up by amateur astronomers or professionals, both. And this year, it's on September 14th. So please mark that on the calendar. And if you want to find out more, I have some postcards with me. Please grab those afterwards, or you can just go to moon.nasa.gov. I also want to, Alex mentioned earlier the space apps. I was here in October, and I'm getting goosebumps thinking about this because I met this group of young girls from high school. They were the space apps baddies. and they did a lunar-related space app. So I'm super glad that you highlighted that. So, so now we've come time for a very special presentation. And this is going to be about the Great Lunar Expedition for Everyone. So this is it's called GLEE for short. This is one of the GLEE kits. And what it's done with a friend of mine at the Colorado Space Grant Consortium, they have brought getting to the moon, getting an experiment on the moon, in this case a magnetometer, to within reach of high school students and college students. And so there is a school that the African Astronomical Society has decided that it's going to give this to, I believe, outside of Pretoria. And so this is just the first of what I hope is many once we get our partnership going. So I would like to give this and a little instruction kit to Dudazil here it's our honor to give this to you, and please enjoy, and I hope your students take themselves and their science to the moon.
Thank you.
Thank you. Thank you.
Okay, I almost walked away, but thank you so much to the NASA team for the beautiful evening, and especially for this. It means a lot when we can give certain resources to the people in the various communities. And before anyone asks, the reason we did not choose a school in Cape Town is because we're already making so many efforts during this GA to reach out to the Cape Town community. And this is just a small step of trying to reach out to other parts of the country and the continent. With many of the collaborations we are making now, we'll definitely be distributing a whole lot more resources to the many African countries that we have. Thank you so much. This is greatly appreciated.
All right, and that concludes our evening with NASA. Thank you all so much for being here. Another round of applause for all of our speakers. And thank you to the IAU GA for having us. All right, good night.
No, Egypt is full in 2020.
Did someone drop their phone? Someone dropped their phone. It's an honor. It's just an honor. Okay, if you're looking for your phone, please come find me.
So what division are you in, James? Code R or Code T?
Code T.
Okay.
Supercomputing division.
Right, yeah.
basically, so-
Right, because you need the computers to run the different models.
Yeah, I do also kind of like database development
Okay.
and stuff. But you know, many people I know from our division collaborating for this.
Oh yeah, yeah. Like I've been collaborating with a couple of Code T people on machine learning projects.
Yeah. We also do machine learning stuff. Actually, I'm very interested to develop collaboration on the astrophysics side because I kind of have limited